Good day, Madam Mariana and fellow classmates. My name is Wong Leong Yang, and today I will be presenting my mini project for Physiological Optic 2. The topic of my presentation is Add the optical optician with the respective correction method using information technology. My cases focus on analyzing myopia and demonstrating how digital tools can help us make accurate clinical decisions in optometry. To begin, refractive error occurs when the eyes cannot focus incoming light precisely onto the retina. Among the different refractive errors, myopia or short-sightedness is the most common globally, especially among young adults. In myopic eyes, peripheral light rays entering the eyes come to a focus in front of the retina, instead of directly on it. This leads to blurry distant vision, even though near vision usually remain clear. The object of this mini project is to demonstrate how digital tools such as Excel and ray tracing simulator can be used to analyze myopia and determine an appropriate correction method. The project includes a simulate clinical cases, optical principle analysis, digital calculation, ray modeling, and evidence based on correction justification. This is the stimulate cases using in the project. The patient is a 20 years old individual presenting with unaided visual acuity of 6/24, which improved to 6/6 with correction. Retinoscopy and subjective refraction finding reveal a simple spherical refractive error of -3 diopter. The main complaint reported is difficulty seeing distant objects clearly, particularly during classroom learning and while driving. No astigmatism or other complications were noted, making it a straightforward case of mild to moderate myopia. Myopia can occur due to one of two primary reasons. First, the axial length of the eye may be longer than normal. Second, the cornea of crystalline lens may have excessive refractive power. Both conditions cause light ray entering the eyes to converge too quickly, resulting in the focal point forming in front of the retina. To correct this, we need a negative or concave lenses which diverge incoming light so that they can refocus precisely onto the retina surface. The optical principle behind myopic correction can be mathematically demonstrated using two key formulas. The first is the Vergennes formula, L plus F equal to L, which describes the relationship between the vergence of incoming light, the power of the light lens, and the vergence of the outgoing light. The second is the lens power formula, P equal to 1 per F, where the focal length is inversely proportional to the lens power. In this case of myopia, a negative focal length is needed. This confirms that a concave lens will shift the focal point backward onto the retina, correcting the refractive error. For this project, two digital tools were used. First, Microsoft Excel was used to calculate the focal length corresponding to different negative lens power. This helps quantify how different lenses strengths influence the focal point. The second one is an online ray diagram stimulation tool was used to illustrate how a concave lens alters the path of light entering the eye. This digital modeling allows us to validate the optical calculation and visualize the correcting effect of the -3 diopter lenses. The Excel calculation provides a clear comparison of how differentiate negative lens power affect focal length. For example, a -1 lens has a focal length of -1 meter, producing only mild divergence. A -2 lens reduces the focal length to -0.5 meter, creating a moderate divergent effect. Finally, the -3 lens used for our patient has a focal length of -0.33 meters, which is sufficient to shift the refracted focal point back onto the retina. This supports our chosen correction power based on quantitative data. The second digital tool used was a ray tracing simulator from the PhET Colorado. In the uncorrected model, incoming parallel rays converge and form their focal point in front of the retina plane, which accurately represent myopia. When we introduce a -3 diopter concave lenses to the system, the ray divergent appropriately before entering the eye. The simulation then shows the focal point moving precisely onto the retina, confirming that the lens power effectively corrects the refractive error. This digital visualization strengthens the accuracy of our correction plan. The primary correction method recommended for this patient is spectacle with a concave lens of -3 diopter. The chosen lenses material is a polycarbonate, which is lightweight, impact resistant, and provide good optical clarity. The refractive index is 1.59, offering a thinner and more comfortable lens profile. To improve visual quality, the recommended coating include anti-reflective coating to reduce glare, blue light filtering to minimize digital eye strain, and UV protection to safeguard retina health. Spectacles are safe, convenient, and ideal for a 20-year-old patient, providing stable and full field correction. A secondary correction option is soft spherical contact lenses, also prescribed at -3 diopter. Since the refractive error is below -4 diopter, vertex distance compensation is not required. Contact lenses offer a wider field of view, better peripheral clarity, and greater convenience for sport or physical activity. However, they require a strict attention to hygiene to avoid complications such as microbial keratitis because of the need for proper cleaning and care. Not all patients may be suitable candidates for daily contact lenses wear. For patients with stable refractive errors, refractive surgery such as LASIK PRK may be considered. This procedure reshapes the cornea to eliminate the need of spectacle. However, this patient is only 20 years old. Refractive stability may not yet be achieved, and surgery is generally recommended only when the prescription remains unchanged for 1 to 2 years. Therefore, surgical correction is not recommended at this stage. Spectacle remains the safest and most appropriate option. The digital calculation and simulation clearly support the chosen correction method. The actual data show that a -3 diopter lens produces a correct amount of divergence required to shift the focal point onto the retina. The ray diagram simulation visually confirms this by demonstrating the correcting focal point alignment. With the corrective lens, the patient visual accuracy improved from 624 to 66, validating the accuracy of the prescription. This finding demonstrates how digital tools enhance clinical decision making and ensure precise correction. In conclusion, this mini project illustrates the value of combining option principle with modern digital tools. Through Excel calculation and ray tracing simulation, we are able to accurately and analyze the behavior of myopia and determine the optimal correction method. A -3 diopter concave lens was found to be the most appropriate solution for the simulated patient. This approach highlights the importance of technology in optometry, especially for ensuring reliable, evidence-based vision correction. Thank you for your attention.